So to calculate equilibrium constants and the concentrations that go along with them takes a little bit of practice, I won't lie. So I'm going to try and share with you some of the ideas here that might be helpful. So we're back to the H2 and the I2 making 2HI, and 55.3 is the equilibrium constant. So let's say we put a mole of hydrogen and iodine in a 1 liter flask. How does that work out? Let's calculate the equilibrium concentrations. Well, you guessed it, we need an ice table, initial change in equilibrium. Initially, we have 1 mole of H2 and 1 mole of I2 in a 1 liter flask. So the concentrations of H2 and I2 are just 1, and HI would be 0. Then we're going to use the stoichiometry to go to the change part. H2 and I2 will go down by x, and HI will go up by 2x. And that's because there's twice as much of HI being made for every H2 and I2. So at equilibrium, you're going to have 1 minus x for H2, because we don't know what x is, we can't go any farther. I2 will also be 1 minus x, and because of the stoichiometry of 2 by HI, that positive 2x will go down as to positive 2. So it's kind of cool. We're going to have one equation and one unknown, nothing you can't handle. So at equilibrium, you have the HI squared divided by the H2 and the I2. Now, we'll talk about H2 and I2 in just a little bit. However, we want to, on the top there, we want to put 2x quantity squared. It's not 2x squared, like 2 times x squared. It's 2x quantity squared. So it's like 2x times 2x. Now, initially, this reaction right here, it has one unknown, x, but there's a lot of pieces to it. We'd have to solve it as a quadratic, stuff like that. However, in chemistry, it's very common to see a reaction like this where you can take the square root of both sides. So bear with me here for just a second. Square root of 2x quantity squared is like square root and squared. They cancel out. It's just 2x. And in the bottom, you have 1 minus x, and if you multiply them together, 1 minus x quantity squared, well, we're square rooting it, so that goes down to just 1 minus x. And then finally, you want to take the square root of 55.3. Your calculator can do this for you. It comes out to be 7.44. At this point, we'll use the distributive property. 7.44 times 1 is 7.44, and 7.44 times minus x is minus 7.44x. And we can then combine all of the x's, because remember, all of that equals 2x. We will add 7.44x to both sides, so we'll have 9.44x. 7.44 plus 2 is 9.44. 9.44x equals 7.44. We can then solve for x by dividing by 9.44 on both sides. That leaves just x. X is going to equal 7.44 divided by 9.44, and that equals 0.788. Now, from this point, you can figure out the H2, the I2, and the H2. The H2 and the I2 are both equal to 1 minus 0.788, and that comes out to be 0.21 moles per liter. On the other hand, if you're curious, the HI will be 2 times the x. 2 times 0.788 comes out to be 1.58 moles per liter. So these are the values at equilibrium. Here's another kind of reaction. This is dinitrogen tetroxide making nitrogen dioxide with a 1:2 ratio. So the K value, a Kc expression, products divided by reactants, that's going to be NO2 squared divided by N2O4. And this reaction's been studied a lot, so it's 0.0059. So that means this is a very reactant-favored set of conditions, all right? So at the end of the day, we're expecting more reactant than product. So we're starting with 0.50 moles per liter N2O4. What are the equilibrium concentrations then for the N2O4 and the NO2? And this is the kind of question you can absolutely answer. Now, N2O4 is more or less colorless, while NO2 is a very sharp brown. And you can see, like in the pictures in the lower right, the right-hand side one has NO2, and the left-hand side one probably has a lot of N2O4. So it's not really that important for our problem, but it's kind of cool to think about, especially for the stuff coming up. So we'll set up the ice table. Initially, we have 0.50 moles per liter N2O4 and no NO2. And like before, the change part will reflect the stoichiometry. That's a 1 to 2 ratio. N2O4 will go down by x, NO2 will go up by 2x. So at equilibrium, 0.5 minus x for N2O4, and NO2 will be equal to 2x. We need to square the NO2 because of the stoichiometry. So 0.0059 equals quantity 2x quantity squared divided by 0.50 minus x. And this is a problem you can solve. It uses what's called the quadratic formula. It's a pretty easy kind of program to use, and I will certainly pass that along if you're interested. But we do have one unknown and one equation, so let's see how you can solve it. We're going to solve this KC. We're going to have to use what's called the quadratic equation to solve it. And here's what I mean by that. So first of all, let's try and clean this up a little bit. We'll multiply both sides by 0.5 minus x. So the 0.5 minus x in the denominator on the right goes away. But then you have 0.0059 times 0.50 minus x. And that's going to equal 2x quantity squared. Well, 2 squared is 4. X squared is x squared. So that comes out to be 4x squared. Now, 0.0059 will multiply by both 0.50 and minus x. So when you look at this long enough then, the 0.0059 is going to be multiplied by 0.5, and that's where this number comes in, 0.0029. But it's also going to be multiplied by minus x. So you can see right there, you've got a minus 0.0059x. It's minus x, so that's where the negative comes from, but this is the idea. And all of that, of course, equals 4x squared. So when you rearrange this, and usually the x squared value is a positive number, by the way. But anyway, the number in front of the x squared is certainly positive when you write it like this. So 4x squared plus 0.0059x minus 0.0029 equals 0. Now, the quadratic formula always looks like this. It's an ax squared plus bx plus c equals 0. And that's what we have here. So in this problem, a equals 4, b is 0.0059, and c is minus 0.0029. The quadratic formula is minus b plus or minus square root b squared minus 4ac over 2a. And that's where those values come from then when you figure them out. So for example, this is what the quadratic formula filled out would look like. You can see you've got the opposite of b plus or minus square root b squared minus 4ac over 2 times some kind of an a factor. So in your calculator, when you solve this, and I'm going to encourage you to do this, at the very end, you're going to get 2 answers. You're going to get 2 answers because of this plus or minus part right here. So when you do this, either manually or in your calculator, as I'll talk about, you end up with x equals 0.026, and you're also going to end up with x equals minus 0.028. But the good thing about chemistry is that because we're all based on moles per liter, like in the ice table, and moles per liter is based on moles, which is based on grams, you cannot have negative mass in chemistry. There are no negative numbers for mass, moles, molarity, stuff like that, because that's just talking about then turning something positive, a positive mass, into a negative mass, and that doesn't exist, at least in our universe. So for this problem, you don't want anything to do with the negative root. Just ignore it. X is only going to equal positive 0.026 because that's where matter is, always positive numbers. So the N2O4 will be 0.5 minus X. That comes out to be 0.47 moles per liter. And the NO2 will equal 2 times the X, 2 times 0.026, and that'll give you 0.052. So you're good to go. Now, in the 21st century, the solve function on calculators can be really, really helpful. And if your calculator has a solve function, you can make mincemeat of these quadratic formula problems. And I encourage you to check that out if you want. If you do this problem correctly, you should end up with 2 same answers as I do, all right? If you don't see these numbers, of course, let me know. If you use the solve button, though, I want you to report both roots, not just the positive root, but I also want you to report the negative one. And you can say, that's lame, doesn't do anything or whatever, but make sure that you report them both, all right? Not just the answer that I'm looking for, but report both of the roots.